In this video, we're going to look at another example of volumes by slicing. The question here is to find the volume of a right circular cone with height h, lower base radius capital R, this is a lower base radius, and top radius R, this is a top radius here. The top of the cone is cut off parallel to the base, and our goal is to find the volume of this solid. So the first step, as usual, is to draw a picture of the solid and the cross-sectional area slice. So the solid is drawn here, and you can see the top of the cone is cut off. The height is basically h, this is the height. And our goal is to find the cross-sectional slice perpendicular to the direction in which we will add them. In this case, it's perpendicular to the height. We're going to add up these slices in the y direction and find the volume of the solid. So we have drawn an outline of the solid in the xy plane, and you can see that the cross-sectional slice is here. This is the cross-sectional slice, and these slices are essentially circles. We're going to add up all these cross-sectional slices in the y direction, integrate with respect to y, to find the volume of this solid. All right, so what we have is the cross-sectional slice at height y is a circular disk with radius. The radius of this circular disk is equal to x, where y ranges from 0 to h, the height of the solid. So let's solve for x in terms of y because we need the cross-sectional slice as a function of y. We're going to start by using the equation of a straight line. Y minus y1 is equal to slope m times x minus x1. Y minus 0 is equal to slope. Slope is rise over run, so it's going to be y2 minus y1, h minus 0 over x2 minus x1, small r minus capital R, times x minus r. If we rearrange this and solve for x in terms of y, doing a bit of algebra, we get x is equal to capital R plus little r minus capital R divided by h times y. The key concept is that the cross-sectional area slice at height y is a circular disk. There it is. The circular disk is a circular disk perpendicular to the y-axis. And the radius of this circular disk is x. So we need to find the cross-sectional slice as a function of y, integrate a of y in the y direction to find the volume of the solid. So basically, we're going to integrate a of y dy from 0 to h to find the volume of this solid. All right, so the next step is to find a formula for the cross-sectional slice as a function of y. The slice area is equal to pi times radius squared. What is the radius? The radius is x. Look at the diagram. This is the radius. Radius is x. So it's going to be pi times x squared. But we need this slice area, this cross-sectional slice area that is perpendicular to the y-axis. We need this to be a function of y, not x, because we're going to integrate in the y direction. We're going to add up these cross-sectional slices in the y direction. So let's apply the equation of the line joining the bottom disk to the top disk. And the equation of line was solved before, and we isolated for x. X is equal to r plus r minus capital R divided by h times y. The cross-sectional slice, a of y, is equal to pi x squared. This is equal to pi times r plus r minus r over h times y all squared. Now that we have found the area slice a of y, this will form the integrand of the volume formula. And the volume formula for the slicing technique is volume is the integral from c to d. In this case, we're integrating with respect to y because we're adding up the cross-sectional slices in the y direction. So a of y dy. Where the lower limit of integration, in this case, is c. C is equal to 0. That's the lower y limit of integration. And d is the upper y limit of integration, which is h. All right, and a of y, of course, is all of this. All right, now we have to integrate the area slice, the cross-sectional area slice a of y, to find the volume. So volume is integral from c to d a of y dy, c is equal to 0, d is equal to h, that's the upper limit of integration, and the cross-sectional slice a of y, and the cross-sectional slice as a function of y, is pi times capital R plus R minus capital R divided by h times y all squared. So now it just remains to integrate. Volume is equal to integral from 0 to h pi times radius squared, so R plus R minus capital R divided by h times y all squared dy. We're going to apply U substitution to make the algebra easier to do. So of course we can open this up and integrate using the reverse of the power rule, but it would just be too messy. So we're going to apply U substitution. We'll let U be the inside function, this part here. So U is equal to R plus small r minus capital R divided by h times y. Differentiate both sides. Derivative of capital R is just 0 because it's a constant. So we get R minus R over h times dy. And now if you solve for dy in terms of du, we get dy is equal to, flip this part here, we get h divided by R minus R times du. All right, we also have to change the y limits. So change y limits to u limits. Because we're doing the method of U substitution, if you change your variable, the limits have to change as well. Change y limits to u limits. So y equals 0, plug it into u is equal to r plus little r minus big R divided by h times y. Plugging y equals 0 in, we get u is equal to capital R. Now plug y equals h. The upper limit of integration, we get u is equal to, and y equals h, we get r plus little r minus big R over h times h. The h's cancel out, and we get capital R minus capital R, that's 0, so we just get r. So u is equal to small r. So the volume is equal to pi times h over r minus r. Integrate from capital R to small r, u squared du. Now this is easier to integrate. All right, so what we have is volume is equal to pi, integral from 0 to h, reviewing what we did, capital R plus R minus R divided by h times y all squared dy. This is equal to pi times h over r minus capital R, integral from r to small r, u squared du. So the volume is equal to pi times h divided by r minus r. And if we integrate u squared, that's just reversing the power rule, we get u cubed divided by 3. Evaluated from capital R to r. Let's simplify this. We get pi h divided by 3 times small r minus big R. Now apply fundamental theorem of calculus, putting the upper limit in, we get r cubed, minus the lower limit is capital R cubed. Now let's apply the difference of cubes to simplify this. The difference of cubes is a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So we can rewrite this part here, r cubed minus capital R cubed, as equal to r minus r times small r squared plus r times capital R plus capital R squared. So the volume is pi h divided by 3 times small r minus capital R times r minus r. Now we use the factored version using difference of cubes times r squared plus small r times capital R plus r squared. Now we have a common factor that's going to cancel out. That was the whole point of applying difference of cubes. So volume is equal to pi h divided by 3 times r squared plus little r times big R plus r squared. This is the volume of the solid, that we had on page 1. There it is. That's the volume of the solid. All right, thanks.